I have a pleasure to participate in this conference. I'm Ibrahim Idir, PhD student in the Laboratory of Electronic Signal Processing and Physics Modeling at the Faculty of Science of Agadir from Ibn University. I'm going to talk about the development of a gas microsensor based on nano-structured zinc oxide thin film for ethanol gas detection. So, a simple plan for my participation. Firstly, I'm going to introduce some information about the gas sensor, thin films, and fabrication technique. Then I will speak about methodologies. So after, I will discuss the same results. And finally, I'm going to finish it with conclusion. As we know, gas sensors are currently of great interest in several fields of agriculture, safety, industrial, chemical, and petrochemical process to avoid the interaction of employer working in situ with toxic, flammable, or explosive species. For example, gas leak detection, biomedical diagnostics, and food quality. Metal oxide gas sensors get the potential to detect a wide range of gases and vapors due to their compatibility with a variety of production metals. Among them, zinc oxide, which exhibits remarkable properties as its non-toxic, high sensitivity, low cost, and miniaturized size such as thin films. So, several techniques have been used to synthesize zinc oxide thin films, including chemical vapor deposition, chemical bath deposition, spray pyrolysis technique, electrodeposition, or cellar method, abbreviation of successive ionic layer adsorption and reaction. In all this work, we choose cellar technology due to its advantages such as low temperature, simplicity, reproducibility, and this method provides optimal fabrication conditions to obtain high-quality zinc oxide thin films. For the methodology, we have manufactured a gas microsensor based on zinc oxide thin films using cellar technique. The deposition of nanocrystalline zinc oxide thin films was performed by successive immersion of a glass substrate in different solutions. For the calcium source, a solution of a mixture of zinc chloride and ammonia. The second solution is hot distilled water. The third one is hydrogen peroxide solution as anion source. And finally, ultrasonic treatment in a distilled water bath. The films prepared are thermally annealed at temperature of 400 degrees C for an hour with a heating rate of 5 degrees C for a minute under ambient air. The measurement system consists of three parts. The first is sampling part, where the equipment set for air generation and control. The second is measuring part, consists the cell where the sample to be analyzed is injected, and the last is acquisition and processing part. In our case, we use an Arduino Omega card with the LabVIEW program. So, the test protocol passes through three steps: sensor stabilization under air, target injection under air, and sensor recovery under air. The performances of the sensors are characterized by different parameters, namely response, stability, response time, which correspond to the time necessary to have 90% stabilization, and recovery time, which correspond to the reaction time following the removal of the gas. Now we discuss the results part. From the first scanning electron microscopy analysis, we noticed that the films are made of nano-sized grains homogeneously distributed on the substrate surface. The images were subsequently processed by image software to determine grain size distribution. The average grain size measured from scanning electron microscopy images increases with the number of growing cycles. From the X-ray diffraction analysis, we observe that the films produced are pure and well crystallized in the hexagonal phase. The nano-sized crystallites tend to agglomerate into larger grains following the film post-thermal annealing, which is in a good agreement with the recent evolution of grain size of zinc oxide reported by scanning electron microscopy. The intensity of the peak 002 was found to rise in proportion to the number of cycles as shown in this figure. This phenomenon is explained by the increase in film thickness as the number of cycles increases, with an improvement in crystallinity and film homogeneity. This was accompanied by a decrease in peak half-width, indicating an increase of the zinc oxide crystallite size from 27 to 34 nanometers, as the number of deposition cycles increased from 10 to 14. So, to get the gap energy of our material, the UV-Vis analysis is performed and showing that the band gap value varies from 3.2 to 3.8 electron volts. Also, we can see that the gap energy of the films decreases with increasing thickness as the number of cycles increases. Obtaining sufficient thermal energy will be necessary to overcome the barrier of activation energy for chemical oxygen absorption and surface interaction. Therefore, in order to optimize the energy consumption of the sensor and to limit the thermal degradation of the detection material while keeping a good response of the sensor under the target gas, we choose to work with the thicker films due to the low gap energy. In this slide, we have the electrical response of the zinc oxide sensor. We have the response under activated gas at a temperature of 300 Celsius. There is a decrease in the resistance of the sensor under ethanol as shown in the right figure. The left figure describes the sensing mechanism. Under air, the absorbed oxygen is bound to the surface and gives an initial potential barrier. When ethanol gas is injected, it reacts with the absorbed oxygen species and causes the liberation of the carbon dioxide, water, and electrons. The separation of electrons leads to a decrease in the resistance of sensor. The following figure shows the responses and the response times for all concentrations of ethanol gas. The response seems to increase with increasing of ethanol concentration, specifically at 60 parts per million. The response time is less than 60 seconds. As a conclusion, we have successfully fabricated a gas sensor using the solar technique. Then we have explored the sensor properties under different ground conditions, also the evolution of the grain size as function of the number of cycles. Finally, we found that the sensor with 40 cycles showed good detection capability for ethanol gas sensing in terms of affinity and response time. For perspectives, the system should be further improved by testing the effect of other growth and annealing conditions, testing the sensor under photoactivation conditions, and integrating powerful UV leads for different wavelength and frequency. Finally, thank you for your attention and I hope you are doing well and your family.